Welcome to all. So today we will discuss about transformer on loaded condition. Previously we have discussed that what will be the phasor diagram of transformer when there is no load at the secondary side. So now we will discuss, as soon as we connect a load in the secondary side, a current I2 will start flowing through this secondary winding, which was initially 0. When there was no load in the secondary side, the I2 was 0. So now a current I2 will start flowing through this winding, since N2 is the number of turn in the secondary winding. So an additional MMF, that is N2 I2, will be generated over here, and because of this MMF, an additional flux phi2 will start flowing through this core also. So this additional flux phi will try to weaken this original flux phi m, जो हमारा पहले प्राइमरी वाइंडिंग के करंट की वजह से फ्लो हो रहा था. Now this additional flux will try to weaken this flux phi m. So we should neutralize the effect of this MMF N2 I2. So because of that, we need to have some extra current from the primary winding, like we need to have some extra current. Suppose initially it was I0, and now after the connecting the load, the current becomes I0 plus this one. Yes, so initially when there was no load, the current was I0, the primary current was I0. So now the current must be I0 plus I1 dash. So this I1 dash, the value of this I1 dash must be such that the MMF, that is N1 I1 dash, should be in equal and opposite direction of N2 I2, so that the effect of this N2 I2 can be neutralized. So this is the working of the transformer with the loaded condition, that an additional current I1 dash will start flowing through the primary winding. So initially it was I0, and now the primary current, the resulting primary current will be I0 plus I1 dash. So see here that our flux phi m is again, it is phi m, which was initially, जो हमारा पहले flux phi m था, हमने फिर से वही phi m achieve कर लिया, regain कर लिया, and जो additional flux phi generate हो रहा था, जो हमारी magnetic field को weaken कर रहा था, that additional magnetic flux, the effect of that flux has been neutralized by this additional current I1 dash. Right? So this I1 dash, the value of this I1 dash must be equal and opposite to I2, the I2 current, the secondary winding current. So by this relation we will draw the phasor diagram of this transformer with on load condition. So here we will see the phasor diagram. This is the phasor diagram of transformer when the load is lagging, means the load is RL load. So first draw the flux phi, because flux phi is always drawn the reference axis, because phi is common for primary and secondary side, right? So all the primary side currents and voltages will be drawn over here, and all the secondary side voltage and current will be drawn over here, right? And this is the reference axis where flux has been drawn, because the flux is common for both primary and secondary side. So first of all, draw the flux on the reference axis. Then we know that E2 and E1 EMFs are lagging behind the flux by 90 degree. So draw E1 and E2 over here. Since E2 is equals to V2, if we are considering the ideal transformer, then E2 is equals to V2. So V2 is also has been drawn on the same axis. Now V1 is equals to minus E1. So V1 will be drawn just opposite direction to the E1. So V1 is has been drawn over here. This is V1. Now I0 will be the current. So actually this is I0. I0 is the current, primary winding current. This is suppose lagging load, RL load. So I2 will be lagging the voltage V2 by an angle phi 2 degree. So we will draw, after V2 we will draw I2, and in the just phase opposition of I2 there will be I1 dash, as I have discussed that I1 dash will be in phase opposition of I2, and the resultant of this I1 dash and this I0 will be equal to I1. So this is our primary current I1. This is actually I1, which is a resultant of I1 dash and I0. This is I0. So this is the phasor diagram of the ideal transformer on load condition when the load is connected on the secondary side. So if this is a pure resistive load, then this I2 will be on the same axis on V2. So I2 will be here for resistive load, right, and I1 dash will be here, because on the phasor position of I2 will be I1 dash would be here, and I1 will be the resultant of I1 dash and I0. So I1 will be somewhere over here, right, when the load is capacitive load. So for leading load, for leading power factor, I2 will be here. When I2 will be here, then I1 dash will be in the phasor position of I2, and the primary current I1 will be somewhere here, the resultant of I1 and I1 dash and I0, right. So this is the phasor diagram of ideal transformer on load condition. Now we will come to discuss about the practical transformer. So this is the basically circuit diagram of a practical transformer. It is not an ideal transformer. We can see here that there is a resistance. This is called as the primary winding resistance R1, primary winding reactance X1, primary winding current is I1, V1 is the supply voltage, E1 is the induced EMF in primary winding. Now on the secondary side, V2 is the load voltage or terminal voltage, R2 is the secondary winding resistance, X2 is the secondary winding reactance, I2 is the secondary winding current, E2 is the induced EMF in the secondary winding. So this is actually the circuit diagram of actual transformer or practical transformer. In the ideal transformer, these R1X1 and R2X2 are absent. So in that case, V1 is equals to minus E1 and V2 is equals to E2 in ideal transformer. But now in this case, E2 will not is equals to V2, but V2 will be equal to E2 plus I2 Z2, where Z2 is R2 plus JX2, right. Like over here, if we apply KVL in this circuit, then V1 is equals to I1 Z1 plus E1, where I1 Z1 is R1 plus JX1. So this is basically the circuit diagram of a practical transformer. Here you can see the reactance of primary and secondary X1, X2, Z1, Z2, impedance of primary and secondary. So Z1 is equals to R1 plus JX1 and Z2 is equals to R2 plus JX2. Same, apply KVL on the both sides. We will be having the voltage equations of the transformer. Apply KVL on the secondary side, we will have the voltage equation like this. V2 is equals to E2 minus I2 Z2 and V1 is equals to I1 R1 plus I1 X1 plus V1 dash, where V1 dash is equals to minus E1. Always remember that V1 will be minus E1, always will be having the sign of minus with E1. So apply KVL on the secondary side, we will having this equation. Now the steps to draw the phasor diagram of the transformer, just remember these steps. It will be very easy to draw the phasor diagram of a transformer. First step is consider flux phi as a reference vector. As I told you that phi is always drawn as a reference because it is common for primary and secondary winding. Draw vector E1 lagging phi by 90 degree. Draw vector E2 in phase with E1. Right, so first of all draw E1 lagging by 90 degree and then draw E2 in phase with E1. Extend E1 in opposite direction and mark is at minus E1, that will be equal to V1. Draw the vector I mu or Im along phi and IE or I omega along minus E1, then draw their resultant I0 making an angle phi naught with minus E1, then draw the vector I2 lagging E2. So these are the basic steps for drawing the phasor diagram of the transformer. Then draw I2R2 in phase with I2 and I2X2 perpendicular to I2R2. So I will show it to you with the help of one phasor diagram. This is the phasor diagram for lagging power factor. If for practical transformer or actual transformer, if we are having RL load, lagging power factor, RL load means lagging power factor. So first of all draw flux phi over the reference axis, then E1 is equals to E2 on this, E1 is equals to E2 lagging behind, this phi by 90 degree. In ideal transformer we have drawn V2 also over here, but here V2 is what? V2 is equals to E2 plus I2Z2. So V2 will be some here. So suppose this is your I2 and this is your V2, right? So I2 R2 will start from V2 and in phase or in parallel with I2, right? So I2 R2 will be in phase or in parallel. We can use a parallel diagram over here. So I2 R2 will start from V2 and in parallel with I2. This is I2 R2. I2 X2 will start from I2 R2 and having 90 degree angle from I2 R2. So this is I2 X2, right? So this is your V2 plus I2 R2 plus I2 X2 is equals to E2. This is the resultant E2, and I2 will be over here with having an angle some phi 2 degree with V2. So this is all about the secondary. Now we will come to primary side. How we will come to primary side? Whenever there is I2, in just opposite direction there will be I1 dash. So in here this is I1 dash and I1 dash and I0, the resultant, that is I1. So this is the primary current I1, the resultant of I1 dash and I0. Now in the same parallel with I1 and starting from minus E1 there will be I1 R1. So I1 R1 will be having in the same phase of I1 and this will start from minus E1, right? And from I1 R1 there will be start I1 X1 and having an angle of 90 degrees. So I1 X1 will be here and the resultant of minus E1 plus I1 R1 plus I1 X1 will be V1. So this will be your V1. So this is how the phasor diagram has been drawn for a practical transformer with lagging load when the load is RL load, right? So similarly we can draw the phasor diagram for leading power factor or for RC load, and for unity power factor means for resistive load we can draw the phasor diagram. Okay, so this is the equivalent circuit of the transformer on no load condition. So this is the equivalent circuit of ideal transformer on no load condition, and on load condition this is the equivalent circuit of the transformer of practical transformer on load condition. So this is the core parameters R0, X0. This is the winding. R1 is the primary resistance, primary winding resistance, primary winding reactance. R2 is secondary winding resistance, and this is secondary winding reactance. Right. So this is the basically the circuit diagram of transformer on loaded condition, the circuit diagram of practical transformer or actual transformer. Now in the next lecture we will discuss how we can refer these transformers, these the equivalent circuit of transformer, either on primary side or on secondary side for the sake of simplicity of the calculations. Thank you.